Now we have seen the Fourier transform of the basic signals. If you want to find out the Fourier transform of the any complex signal, again you have to go by the usual method, that integration and all, it will become very difficult. So for that, another solution is to understand the properties of the Fourier transform. If you understand the properties of the Fourier transform, and if you know the Fourier transform of the basic signal, you can find out Fourier transform of any complex signal very easily. So till now, whatever we have seen, that thing and the properties, only two things are very important. So now we are going to discuss about the properties of the Fourier transform. Mostly the properties of the Fourier and the Laplace are the same. So this is the notation which is used for the properties of the Fourier transform, that Fourier transform of the x of t is x of j omega. In some of the book they have used x of omega. In some of the book they have used as a x of j omega. You can use anything. Here we are using x of j omega. And inverse Fourier is represented by f inverse of this inverse Fourier transform is a x of t. And in general, x of t and the x of this j omega will form the Fourier pair of each other. It means Fourier transform of x of t is x of j omega. Inverse Fourier of x of j omega is the x of t. Now the first property is a linearity property, which is important, and mostly for all transform, this linearity transform is applicable. The linearity property states that if the signal satisfies the superposition principle, then this linearity property will be applicable for the Fourier transform. Linearity means when the two signals are added in the time domain, that x1 of t plus x2 of t, and they are weighted by any values, that a1 and the a2, it will be anything. If two signals are added in your time domain, okay, and if you find out its Fourier transform of the all signal, Fourier transform of the a1 x1 of t plus a2 x of t, so its Fourier transform is a a1 x1 of j omega plus a2 x2 of the j omega. It means if I have the signal x1 of t and its Fourier transform is the x1 of j omega, then x2 of t, its Fourier transform is x2 of the j omega. So if you find out the Fourier transform separately, or if you combine both the signal in the time domain, its Fourier transform is the addition of Fourier transform of the individual signal. So that linearity states, so even you add the signal in the time domain, its Fourier transform is the addition. You can find out the Fourier transform of the signal by finding the individual Fourier transform x1 of j omega, x2 of j omega, and you can multiply by the weighted values a1 and the a2, and if you add this signal, it will give you the Fourier transform of this whole signal. So that linearity property. So this is used at many places. For example, we have found, for example, I have the x of t is equal to e raised to minus 2t u of t plus e raised to minus 5t u of t. So here are the two signals are there separately. So if you want to find out the Fourier transform, so just linearity property you apply. So Fourier transform of this x of j omega is equal to Fourier transform of this signal Fourier plus Fourier transform of this signal. You can add. That indicates that the linearity property is applicable for this. The next property we are going to discuss is about the time scaling. So already in the first chapter we have seen the time scaling. When the signal x of t undergone a change of x of at, so such type of the signal are called as the time scaling signal. Time scaling means the signal is either expanded in the time domain or it is compressed in the time domain. I have the signal, for example, so this is my signal, this is a 1 and this is minus 1, this is my x of t, okay, this is t. So when I want to plot the x of 2t, t by 2, okay, so here the signal it will look like this, okay, so this is the 2, it is minus 2. So this is the expansion. So when the value of a is less than 1, the signal is expanded in the time domain. So if you compare this equation with the x of at, so a is equal to 1 by 2, so when the a is less than 1, it is the expansion. When, for example, if I want to sketch x of 2t, so here the signal is the compressed in the time domain, 1 by 2, it is minus 1 by 2. So this is a compressed signal. Time scaling means the signal is either expanded in the time domain or either compressed in the time domain, that is called as the time scaling. So when the signal is compressed, if the Fourier transform of the original signal, that the x of t, its Fourier transform, or it is a Fourier pair of x of j omega, then the Fourier transform of x of at is equal to 1 upon mod a x of omega by a, where the omega is a frequency. When this value of a is greater than 1, so accordingly, it is omega by a. So if it is less than 1, again 1 by 2, for example, it will multiply here, it will be 2 omega will be there. So that shows when the signal is compressed, in time domain, when the signal is compressed in the time domain, you see here, when the signal is compressed in the time domain, so that is equivalent to, it is expanded in frequency domain. The significance of this property is that when the signal is compressed in the time domain, it is expanded in the frequency domain. When it is expanded in time domain, it is compressed in frequency domain. If you perform some operation in the time domain, some different operations will get performed. So just to remember, accordingly we can find out the Fourier transform of any complex signal. So this is a time scaling property. Next is a time reversal property. When the signal is reversed in the time domain, its Fourier transform is also reversed in the frequency domain. If Fourier transform of this x of t is a Fourier pair of this x of j omega, then Fourier transform x of minus t, which is a time reversal signal, so this is equal to x of minus j omega. If signal is reversed in the time domain, its frequency spectrum is also reversed. The next important property is the time shifting property. So all of you know the time shifting means it is equivalent to shift the signal in the right direction or equivalent to shift in the left direction. We have seen original signal, for example, I have x of t is equal to e raised to minus at into u of t. So this is my exponential signal. Okay. So the time shifting means the signal x of t, if it is represented by x of t minus t0, it is called as the time shifting. So depending on the values of t0, the signal is either shifted in the right direction or either shifted in the left direction. So this is called as the shifting value. So if the signal is shifted in the time domain, then its Fourier transform is, its original Fourier transform will be as it is, multiplied by e raised to minus j omega t0, e raised to minus j omega t0. That means that, so if you see the Fourier transform, that x of t is the Fourier pair of x of j omega. So the magnitude spectrum for this signal is the x of j omega. It is a magnitude spectrum of x of t signal, and the magnitude spectrum of the time shifted signal, so it is also the x of j omega. That means that if the signal is shifted in the time domain, its magnitude spectrum, remember, its magnitude spectrum remains same. Magnitude spectrum remains same. However, its phase spectrum changes. That is, there is a linear shift in the phase by the omega t0. That is the omega t0. That is the significance. Sometimes they may ask you what is the importance of the time shifting property. The importance of the time shifting property is that if the signal is shifted in the time domain, its magnitude spectrum is going to remain same. However, its phase spectrum will undergo a linear phase shift in the frequency domain. So that is the significance of the time shifting property. So here you remember this time shifting property. So next is a frequency shifting property. Already we have seen that Fourier transform of e raised to j omega 0 t. The Fourier transform of e raised to j omega 0 t is 2 pi del of omega minus omega 0 plus del of omega plus omega 0. So accordingly, if you look at this, if the signal original is x of t, okay, so its Fourier transform is x of j omega. When a signal in the time domain is multiplied by e raised to j omega 0 t, when the signal is multiplied by e raised to j omega 0 t, So its frequency also changes, that it will undergo a change in the omega minus omega 0. This is called as the frequency shifting. When you multiply it by e raised to minus j omega 0 t, it will be omega plus omega 0. So when you want to shift the frequency, so you have to perform some operation in the time domain, that is a multiplication operation. You multiply the signal in the time domain by e raised to j omega 0 t, that is equivalent to frequency shifting. So we have seen in the amplitude modulation, when the signal x of t is multiplied by, that is a sine omega ct, where the omega c is called as the carrier frequency. This omega ct sine can be written as e raised to j omega ct plus e raised to minus j omega ct. So your original frequency is omega is there. So this will change to omega minus omega 0 and the omega plus this omega c. Means the carrier signal is added. The low frequency signal is boosted to the high frequency signal. Accordingly, the modulation will take place. Therefore, this particular property is called as the modulation property. Once again, that is, if the signal is multiplied in the time domain by e raised to j omega 0 t, so it is equivalent to shift in the frequency, which is called as the frequency shifting property. Okay, the Fourier transform of the derivative of the signal. So here it indicates, so x dash of t is equal to d by dt of x of t. That is the first order derivative. When the signal, that if you Fourier transform of the signal x of t is a x of omega, okay, this is x of j omega, then Fourier transform of derivative of the signal, right? Fourier transform of this, the d by dt of x of t. So this is equal to j omega into x of j omega. So if you take the derivative, it is equivalent, its Fourier transform is equivalent multiplying the Fourier transform of the signal by j omega. So accordingly, you can find out if the signal, it will be asked to you to find out the Fourier transform of derivative of the signal. You find out original Fourier transform and you multiply j omega, that will give you the Fourier transform. If it is a second order, the j omega raised to 2 will be there. It is a nth order, j omega raised to n will be there. Accordingly, you can find out the Fourier transform of the nth order of any signal in the time domain, that x of t, that x of n. So accordingly, j omega raised to n into x of omega. Next property is Fourier transform of the integral signal. If the signal is integrated in the time domain, that minus infinity to infinity x of t dt, and if you want to find out Fourier transform of this integral signal, so its Fourier transform is x of j omega multiplied by 1 upon j omega. So accordingly, just you multiply by 1 upon j omega, that will give you the Fourier transform of the integral signal. Okay. So next property is derivative of the Fourier transform, the derivative of the Fourier transform. So if this property indicates that it is same, I will write the Fourier transform of the t into x of t. So this is equal to d of d omega, okay, into 1 upon this minus j, where 1 upon minus j, it will go to the numerator. So it will become the Fourier transform of this t, okay, into x of t, okay, is equal to 1 upon this minus j. So if I multiply and divide by the j, so this will be the j divided by minus j into j, it will be same into d by d omega into x of omega will be there, okay. This, the j square will become minus will become plus, that j into d by d omega of the x of omega, that Fourier transform of the t into x of t is equal to j into d of d omega of x of the omega. That means that if the signal is multiplied, that means the signal is multiplied in the time domain by the t, the signal is multiplied by time domain in the t, that is equivalent to its Fourier transform is j into d by d omega of x of omega. This is called as the derivative of the Fourier transform. If in the frequency domain the signal is, the derivation of the frequency domain is taken, that is equivalent to multiplying the signal in the time domain by t. We have discussed different properties of the Fourier transform and Fourier transform of the basic signal. Just we will revise, because the signal in the time domain, its Fourier transform, if you know, so such type of the question will also be asked in the GATE examination. So it will help you to quickly find out the answer. So you can prepare such kind of table, and if you remember, you can recall it very easily in the exam. So just Fourier transform e raised to minus at u of t is 1 upon a plus j omega. E raised to at u of minus t is 1 upon a minus j omega. E raised to minus a mod of t 2a upon a square plus omega square. T into e raised to minus at u of t. If the signal is multiplied in the time domain, it's a derivative in the frequency domain, 1 upon a plus j omega square. T raised to n, that is n factorial a plus j omega raised to n plus 1. Del of t, its Fourier is 1. Fourier of the 1 is 2 pi del of omega. Fourier of e raised to j omega 0 t is a 2 pi del of omega minus omega 0. So it's very easy to remember. Just you draw the table and recall all these values. Fourier of the cos omega 0 t is pi del of omega minus omega 0 plus del of omega plus omega 0. Similarly for sine, for the u of t we have seen pi del of omega plus 1 upon j omega. For signum of t, it is 2 upon j omega. When it is multiplied by u of t, first you find out the Fourier transform of u of t, convert the cos to the exponential function, use that e raised to j omega 0 t property. So you will get Fourier transform of cos omega 0 t u of t. You remember here, Fourier of the cos omega 0 t is different. Fourier of the cos omega 0 t u of t is different. Fourier of sin omega 0 t is different. Fourier of sin omega 0 t u of t is different. Then it is multiplied by e raised to minus at. So you can use the property, you can find out Fourier transform again e raised to minus at. The 16 signal, mostly in any exam, the Fourier transform of such all from out of 16, some of the problem will be asked. So if you practice, you can easily solve the problem on the Fourier transform of the basic signals. So these are also Fourier transform of some advanced signal. So accordingly, you can find out this I have summarized. So any problem will come from these things. Now next we will see the numericals on the Fourier transform of some complex signal by using the properties and Fourier transform of basic signals.